Hello everyone. We will move to the second lecture of electronic devices, that is energy band diagrams. Now, energy band diagrams, what we see in the first lecture, that what should be the energy band diagram, how it look like for semiconductors, for conductors, and for insulators. But how is energy band diagrams has been formed? What is the basic physical interpretation? What is the reason behind the formation of energy band diagrams and how it is formed? So moving to the next part, we have how the energy band diagrams has been formed. As we all know that every atom in the physics world has this power density functions. Okay, so for hydrogen atoms we have the these function as we increases, like this is the energy functions, this is the energy, and this is the distance between the different different atoms. Now as we see, we have different orbits, like we have p orbit and s orbit, energy orbits. As we increase, as we see that these orbits are increases, the energy has been changes, and as the lower orbit has been increases, the energy also changes. As there is a distance, or there is a point that will come where these energies have been intersected, and as this intersected, this will again go like this, and this will again, the energy will go like this. So this is the point, this is the point, this is again go like this, and this is the point has been which we called has been chosen as the energy band diagrams of a system. So it is a wave function of the electrons of two atoms which will overlap, which means the two electrons, one is the lower energy bonding and one with the high energy bonding with anti bonding orbital energy. These has been interact, and there is a discrete quantizations and levels has been manufactured. Now the splitting of these discrete states in two states is consistent with the Pauli exclusion principles. Now the probability density function of the these isolated hydrogen atoms has been shown that as the energy level increases, there is a point that there is a point at which the number of charge carriers present in or number of electrons present in that energy level. So as we know, this has the highest energy level, so it has the probability that at which that there is too much probability that the number of electrons will possess in that energy level. So this point has that it has number of how many number of energy level, how many number of electrons present at that energy level. Okay, so as we see is that as the hydrogen molecules has been formed, if we see this that that means that as we increases, then at that time, due to the atom, due to the there is two atoms present, so between the two atoms there is a collision, and due to that collision there is a potential well has been created. There is a potential well has been created between the interaction of two energy levels. So that potential well has been created, which contains the highest energy at the end, and it is at the lowest energy at the top. So these potential well possess the energy due to the overlapping of two atoms. So as we increases, the formation of energy levels has been created. Now at as the interatomic spacing decreases, as the interatomic spacing has been decreases, the energy level is split into the bands. Now these are the, suppose like I already told you, suppose we have these energy bands. This is the energy bands, and as we moving towards this is the splition of energy bands. This is the splition of energy bands, and at this splition there is a conduction band, and this is the valence band has been created. Now for all the outer shell electrons, have been conducted here in the valence band, and all the energy states at the conduction band has been empty. So at 0 Kelvin, the electrons will occupy the lowest energy states, and in silicon crystal the valence band exactly have the 4 n states and 4 n electrons to occupies it. But while in the 4 n state of the conduction band will remain empty. So this means that as the distance increases between the atoms, there is a splition of energy bands. The energy states, sorry, not energy band. The energy states will split and will form the energy bands. Now in metals and semiconductor, how will it behaves? Like in semiconductor, at 0 Kelvin, the valence band is completely filled and the conduction band is completely empty. So if the electric field, if you apply electric field, now if we apply electric field, then the valence band have no electrons, will move as no vacant state in the in which electron could move. But in conduction band, there is no electron is present, so no question of electron movement. Although all states are vacant, but there is no electron present in the conduction band. So at 0 Kelvin, what we have, the silicon has highest resistivity, or we say that the semiconductor is behave like a insulator. But in some smaller band gaps of semiconductors that allow for smallest excitation, as the excitation came for electrons, the electrons will move from the valence band to conduction band by the reasonable amount of thermal energy or optical energy, or whatever you have given, that some will apply the electric field or something. So as soon as the electrons in the valence band get that type of energy, like in, thermal energy, thermal agitation, or optical energy, or something like that, the electrons from the valence band will move towards the conduction band. Now based on this, we will see that how the electron and momentum has been increases. Like this is the electron and this is the momentum. Momentum means, in terms of momentum, we will in semiconductor we will say that it is K. How K? That K is shows as the wave function, but as the momentum is also can be used as in terms of momentum, we will see the relation between the energy and the momentum of that charge carrier. So based on the momentum and energies of that of the atom, we will differentiate the semiconductor into a direct and indirect band gap semiconductor. Now in direct band gap semiconductor, what we have, like EK diagrams. Now let me see the some of the EK diagrams, how the EK diagrams work. This is the EK diagram, means there is a slope. Like you see that you found that the slope has been created now. The slope has been created as we move towards this. The slope has been created, that how much the density of electrons or charge carriers present at the top of the the highest energy level, or at the bottom of the lowest energy level. So like it also, every energy level has this curve nature with respect to the momentum and with respect to the energy. So the valence band has the maxima, because it has in valence band it has the maximum at this point, because in the lowest energy levels, as the lowest energy level has been created, as we move towards this, As we move towards this, so this has the maximum here, this is the maximum here, and this is the lowest here, as we see in the last slide. So the conduction band have the minima at which point, and the valence band has the maximum at which point, if this point has been at same momentum. It has same momentum. Now this type of semiconductor is known as direct band gap semiconductor. What we call direct band gap means as soon as the energy, the electrons in the valence band get the energy, as soon as it gets the energy, it will go to the conduction band, but in one direction, and as the energy has been released, the electron will fall to the conduction from conduction band to the valence band, and releasing the amount of energy in the form of light or in the form of photons. So this is something like what we call the the principle we used in the lasers also, like population inversion concept, where there is too much of electrons accumulated at some highest level, and as the energy has been decreases, they will move from the higher energy level to the lower energy level, splitting up given out as the energy in terms of light, but at that time they have the more energy. Here we have a less energy, which energy is equals to this energy is equals to h nu. H nu is what we call hc lambda. Okay, this is the frequency. So this is the wavelength, because photons will move like a wavelength. So this is what we call the direct band gap semiconductors. And what should be the kinetic energy? As we know, the kinetic energy is what? Kinetic energy is half mv square. Half mv square. Okay. So as we saw, if we see, mu is what? Mu is what? C by lambda. Sorry, it is not me, it is the velocity. So we see the velocity of the velocity of electron will be like what? 2 kinetic energy upon m upon under root. And what is this? This is the momentum. How we use the momentum? We know that momentum is what? P is equals to mv. P is equals to mv, and it is what? K square. Like we say that it is what? K square into h square. This is a Planck's constant. And this is equals to what? Half kh square is equals to, half kh square is equals to upon m is energy. Now energy is what? I already told you. Energy is what? Kinetic energy is what? Half m v square. Okay. Now mv square means mv is p. Okay. So what we say that if we multiply here also with kinetic energy, and let me use it somewhere else, like here. Okay. So it is what? Half m square v square, and it is what? It is p, but p is also equals to hk. So it is what? Half. It is also known as p square, or it is also called as half h square k square. So from here we will say that k is what? Momentum is what? Momentum is what? 2 into kinetic energy into m upon h under root h square. Okay, so this formula came from this method. Okay, so this is what we call the momentum of a momentum of photons, or what we call the electrons energy, which will be coming out from when the electrons loses energy and move from the conduction band to valence band. Okay, so now second type is indirect band gap semiconductor. Now indirect band gap semiconductor have valence band maximum at some other point, and the conduction band maximum at some other point. Mean these points are not equal. This is suppose K1, sorry K2, and this is K1. So K1 is not equals to K2. So at different, they will have different maximum and minimum at different momentum. So what will happen as soon as the electrons loses the energy, it will first come at this point. Suppose we will see that it is an electron from conduction band minimum moves from a defect level. It is a some kind of defect level. Okay, defect level. So at some kind of defect level, it will come from the from conduction band to valence band. But how it will loses energy? It will loses energy so that the energy is not too much. Okay, so it will first come out here, then some agitation occur, and there is a combination of some electrons, some pair of electrons. Then again, when there is no external force is applied, so the momentum must be momentum should be satisfied. So from here it will come out as at the valence band. So from the final transition from the defect level to the valence band level, there is a difference, that is ET minus EV and released, and the electrons will released. But in during this state, the photon has been released, but not in the term of light. Not in the terms of light. The heat is releases. Now the example of this, if we see the example of this, we have the gallium arsenide, or we use as a what we call as LEDs. The LEDs causes this type of behavior, means as the temperature, as you give out the energy to the LEDs, it will glow, right? So how it will glow? It will gives the final energy in the terms of photons or some light. So the examples like gallium arsenide, or what we call gallium nitride, depending upon whatever the doping you have given to the semiconductors, it will give that amount of energy, or that amount of what we call color, the wavelength. So because the wavelength is depending upon the energy, so whatever the energy band gap is there, it will directly depend upon the whatever the color you have been given. Okay, so this is what we call the direct band gap, means directly the photons from the minimum of conduction band will flow to the maximum of valence band. But here also there is some see that the momentum is same, so there is not much energy has been released, because the momentum is not changed. So energy has been released, and the most of the energy has been given out in the photons. But if we see the direct band gap, there are two transitions agar. Now two transition agar, so the energy has been released is more, but it is given out in the terms of heat, the thermal agitations. Okay, so if we see the if we point out the difference of the direct band gap and indirect band gap, So first difference is what? First difference is what? If we see that the first difference is same, that the minima of conduction band and maxima of valence band is at same momentum. Means there is no change in momentum, no change in momentum as the electrons fall from conduction band to valence band. Okay, but in indirect, the minima of conduction band and maxima of valence band is at different momentum point. That is, there is a change in momentum as electrons fall from valence band to conduction band to valence band. Okay, so this is one type, or what we call, or what other difference? What should be the other difference? If we see, what should be the other difference? The other difference will be the second difference. The second difference will be the energy will released in the form of light. Will release in form of heat and light. In form of heat and light. The energy is released in the form of heat and light. But in indirect band gap, what we call? Energy will only released in form of heat. Only the energy will release because there is so much transition in between transition occur that the energy is not that much that it will be up to the energy of the photons. So the energy will release in there is only a heat is produced during the transition of, because some energy is released because the electrons will fall from the conduction band to the energy to the valence band, and some type of energy will be released. But since that energy is not up to the energy of the photons, the energy of the photons is some wavelength, right? So that that is not up to that wavelength, because for the photons wavelength it should be some value. It should be some what we call the h nu. It should be the energy should be equal to the h nu. Okay, so that is not the case in the indirect band gap. So the energy will not be up to that mark. Okay, so the energy will release in the terms of heat. Okay, because there is too many transition occur from this position to that position and finally this position. Okay, then if we see the again is third point is the what are the example of direct? We have the gallium arsenide, and for indirect normal silicon diode or normal PN junction diode. Okay, in fact normal PN junction diode it will be used for the indirect band gap. So this is about the band gaps of a semiconductor, which can be used in terms of used in what we call in our semiconductor materials, how the energy band has been formed, changes how the energy, there is a splitting of energy bands from the higher energy level to lower energy level. Okay, so thank you so much.